Here we continue building from our general mechanism for acid-catalyzed nucleophilic acyl substitution. We're going to solve a problem where we work through this type of problem using an acid anhydride as our starting material for the reaction. So this is going to apply the knowledge that we learned from our general reaction mechanism video a couple of videos ago toward this specific problem. Regardless of what type of carboxylic acid derivative starting material you are given, you should be able to work through that general acid-catalyzed nucleophilic acyl substitution mechanism to illustrate how to form the final major product of any reaction. So we're going to apply that here by starting with an acid anhydride. We recognize this as an acid anhydride because of the fact that it has a carbonyl group directly bonded to an oxygen. That oxygen is directly bonded to another carbonyl group, and each of these carbons has carbons or hydrogens directly bonded here. So this is our acid anhydride group right here that I'm circling. Even though it's part of a ring, don't let that throw you off. It's still got that essential component of an acid anhydride functional group. So what we will react with here is we are going to react with methanol, CH3OH. I'm going to give us an excess of the methanol. That is important because we need at least two equivalents for this particular reaction to occur. And additionally, we need, for this reaction to occur, we need a proton source. So we'll go ahead and plug in just proton there. And we're going to work through the mechanism for this reaction. So let's go ahead and get started. First things first, when we have an acid catalyst present, what will happen is that we will get protonation going on first. It doesn't matter which of these two carbonyl sets we work with here in this protonation step. The molecule is symmetrical, so you can take either of those sets of carbonyls, use that to grab a proton. And for purposes of this class, if you are given an acid anhydride, it will generally be a symmetrical acid anhydride, at least in this class, because of the fact that if you had an asymmetrical acid anhydride, you have multiple possible products that could result from analogous mechanisms working on either of the two carbonyl groups. So now that we have protonated, we've replaced then the lone pair electrons on the oxygen with a proton, like so. Positive formal charge goes on that oxygen then. And this was the step that we would have referred to as protonation. Then from there, now that we have protonated, we have created a very capable, very electrophilic carbonyl right here at that location where the carbonyl group now has a proton. And so what's going to happen then is that in step 2, the nucleophile is going to attack that electrophilic carbonyl. And so looking back at our reaction, what we have available as our nucleophile is our methanol. And so methanol will come in, CH3OH. It will use its lone pair of electrons to come in, form a bond to that carbonyl carbon, like so. That forces the pi electrons to go up onto the oxygen to create a hydroxy group out there. So let's go ahead and show the product of this step. Still have our 5-carbon ring intact, at least for now. And now, rather than having a pi bond there, we have a single bond going out to a hydroxy group. We have now a new bond to CH3OH via the oxygen being the link there that connects it to the rest of the molecule, so OCH3. And that oxygen also has a proton attached to it, so I'm going to include that proton. And the oxygen will still have one set of lone pair electrons that are unreacted right here and right here. And now drawing in the other atoms of this 5-membered ring, like so, gives us this. We will have a positive formal charge residing on the oxygen here. We recognize that because our starting structures here had a net total charge of +1, so something over here has to also have a net charge of +1. Calculating in, our oxygen is where that's going to go. So now, at this point, in step 3 of the mechanism, what's going to happen in step 3 is that we are going to deprotonate. So step 3, deprotonation. And what we need to deprotonate is this oxygen atom so they no longer have that positive formal charge in there. And we can do this intermolecularly like we've been doing if we want. And the way that we would do that is we bring in another unit of methanol. Methanol is the only thing that's available in here as a base right now. So methanol comes in, and it's going to use its lone pair of electrons to grab a proton from our acid, from our organic intermediate. That forces the proton-oxygen bond to break. The electrons go onto the oxygen like so. And that's going to lead us to our next intermediate here, where we now have a OCH3 group there, 2 sets of lone pair electrons on the oxygen, and the rest of our 5-membered ring there. Now, at this point, with that acid catalyst present, what's going to happen is now the acid catalyst is going to come in, and the acid catalyst is going to protonate the leaving group. So here at step 4, we're going to write protonate the leaving group. And since this is a ring, sometimes that throws people off about what exactly here is the leaving group. But if we think back to our original reactant, our leaving group, the bond that we are going to break, is always the bond between the carbonyl, what was originally the carbonyl. I'm looking back at my starting material here. So what was originally the carbonyl is what we have in blue. And the bond that always breaks is the bond between that carbonyl and the single bond to whatever the heteroatom is that's bonded there. So the bond we're going to break is the bond that I'm showing in blue here, this one right here in our starting material that we're showing in red, because our carbonyl is always attached to the leaving group. And so coming over here then, when we say we're protonating the leaving group, as we've been doing in the other examples, the leaving group is going to be this oxygen that I just put those lone pair electrons on, because this is the bond that was originally the bond between the carbonyl group and the leaving group. So protonating that leaving group means that we're going to bring in our acid catalyst, move a lone pair of electrons from the oxygen over onto the proton, and that's going to give us our product of this particular step. So we'll have our methoxy group, OCH3, our hydroxy group, OH, and we bring in our oxygen directly bonded to that proton. We still have 1 set of lone pair electrons and a positive charge now on that oxygen after this protonation step. So now that we have done the protonation step, the next step, following our general template for these nucleophilic acyl substitution reactions that are acid catalyzed, is in step 5, we are going to break away the leaving group as the carbonyl reforms. So leaving group leaves as the carbonyl reforms. Same wording here as when we've been looking at these steps before. It might get a little confusing because of the fact that this is a ring, and rings always tend to throw a bit of a curveball. But same principle, that the leaving group is going to be this bond that leads to the positively charged heteroatom. So we're breaking that bond. And as we break this bond, we have to reform a carbonyl. And so reforming the carbonyl would mean taking this hydroxy group lone pair, bringing that down to make a carbon-oxygen double bond. So that then our product of this reaction will have a carbonyl that just has an extra proton on it that we can ultimately break away. So going in and showing this, now our ring will have been broken open, so I don't need to draw a ring. Instead, showing that ring has broken open, the breakage in that ring, I'm going to highlight here this bond that has broken right here. And I'm going to actually number the atoms of the ring so I can keep track of them in the product that I'm going to draw from this. So arbitrarily numbering the atoms of the ring, I'm just going to do 1, 2, 3, 4, and I'm going to number this oxygen as number 5. Because when we take this 5-atom ring and we break that one bond in it, what we're going to end up with is a 5-atom chain. Because if we break this link, that means these atoms, 1 through 5, are still going to be connected together, but they're not going to be no connection between carbon 1 and carbon 5. So I'm going to draw out a 5-carbon chain here. 1, 2, 3, 4, 5. I'm going to number it. 1, 2, 3, 4, 5. And then I'm going to plug in what was present at each of those positions. So at position 1, we had in our starting material a methoxy group and a hydroxy group bonded there. And so therefore, we're going to have a methoxy group in our final product there as well. And at position 1, also that hydroxy group, which actually, since the lone pair electrons came down, became a carbonyl group. So let's go ahead and draw that in. And I'm going to draw this in blue just for emphasis here. So we had our carbonyl group that has the proton on it that was at position 1. So I draw that in. Positive formal charge still on it because nothing's taken that away. And then a methoxy group, OCH3, like so. So that takes care of everything that we see at position 1 here, here, and here. Position 2 had just CH2 groups, so we don't need to fill anything in there. Position 3 likewise had just CH2 groups, so we don't need to fill in anything there. Position 4 had a carbonyl group, so we do need to fill that in at position 4, carbonyl. And then at position 5, we have a hydroxy group. We do not have anything else there other than this hydroxy group at position 5 because we broke that carbon-oxygen bond here in the mechanism. So at position 5, plug in my OH group. And so now to get to our product here, we go onward to step 6. And in step 6, what's going to happen is that we have deprotonation. And in this deprotonation, we bring in another unit of base, which the base that we had available was our methanol. So we bring in our methanol. Methanol uses a lone pair of electrons to grab a proton from our organic intermediate acid, and that's going to create, as a result of this, our product of this step. So we have our carbonyl group, and then our other atoms here and here on over, like so, all the way through to get to here. Now, at this step in this particular reaction, you might think that you're actually done, and you are done on this side, on the left side of the molecule, because on this left side of the molecule, you have replaced the leaving group. That was the carbon-oxygen bond up here in the upper left starting material. That was the bond that broke. You replaced that leaving group with the methoxy group of our nucleophile. So we're done on that end, but this product is curiously yielded at the other end of the molecule in this particular reaction. We have yielded a carboxylic acid group. And we mentioned that there is an excess of methanol. That means all the methanol we could possibly want for this reaction. It helps push the equilibrium toward the side of the products. And what it's also going to do is, you'll recall from the last chapter, that carboxylic acids react with alcohols in acid catalyst to give ester products through a nucleophilic acyl substitution reaction. And so what's going to happen here is that through an additional round of nucleophilic acyl substitution, going back through a mechanism similar to what we just did, we would convert the carboxylic acid group into this ester molecule that has an O-methyl group here, because what will happen is we'd go through a mechanism much like what we were looking at here, through these steps of nucleophilic attack, protonation, deprotonation, etc., and ultimately replace this hydroxy group with the methoxy group from our nucleophile, illustrating to us that the Fischer esterification that we learned in a prior chapter is really just a nucleophilic acyl substitution reaction. So our final product here, I'm not going to go through all the mechanism steps for going from the carboxylic acid to here, our final product, but you should be able to do that if asked to, because the steps are completely analogous to what we're just looking at here, and I would encourage you to draw those out if you are feeling a bit shaky on it. The final product is going to correspond to having replaced that hydroxy group of our carboxylic acid with a methoxy group of our alcohol nucleophile that came in and did a nucleophilic acyl substitution reaction to go from here to here through another iteration of mechanism. So if you were asked to write out the complete mechanism for the whole entire pathway, that would include everything that we've written out here, as well as pretty much doubling it, because we would need to also write out the full mechanism for this nucleophilic acyl substitution that's acid-catalyzed here. And the steps for that would be completely analogous to what we've done as our general acid-catalyzed nucleophilic acyl substitution reaction all along.